All right, welcome back, everybody. It's the final countdown. We're here. We're at the end of lectures, that is. What number are we in? 54. Total brain part. Pre-calc. We are doing 8.8, which is on parametric equations. So, how do I want to say this? A parametric equation. We will have y equals f of x. But this is often related to stuff regarding. Related to time, t. Or angle theta. So like, which means x is really a function of time, x equals x of t. And y is also a function of time, since y is a function of x. They're both functions of time. Like a parabola. Plots the trajectory of something under gravity. Something shot into the air under gravity. Upside down parabola. Shot into the air. And brought back down by gravity. Let's say this is a little cannon and we're firing a cannonball and we're trying to hit a fort. So the way we generally do this is we will have this on the x and y axis, where x is the distance to the fort and y is height of the ball, cannonball. But clearly, at any particular moment, that ball is like, if you were able to fucking down that shit and freeze time, that ball is not moving. It's got a specific x coordinate and a specific y coordinate based on time. So I hear the ball's location is a function of time, both horizontally and vertically. And oftentimes, this is the shit we start with. This is the information we start with. And there's a way, and we're gonna do it, to switch from time to just position. And we say, for this thing, time is the parameter. The parameter is defining everything else. There might be other ones, but time and angle are the really the only two that I've tried to think of, I didn't open a. Like a bunch of textbooks and look up examples to see if there was any other thing that it might be following, but generally it's time or angle. So that's like the idea of what we're working with here, why we're working with it. And well, let's go through some examples here.
So it's, and it's basically an intercept along the line. that we're finding this thing.
If we put them together, kind of. They're gonna start out as two separate equations. We will have two equations. X as a function of time. And y as a different function of time. And so like x will be in terms of t's, y's will be in terms of t's. These are called parametric equations. When you hit calc 3, you'll have z as a function of time. That's the third dimension. And after everyone's done writing down the big picture, we'll start looking at specific examples, that way it'll be much clearer. Wake up, George. You look sleepy. I took 2 naps yesterday. It's fucking glorious. I still managed to grade all the tests for computer science 1. I was pretty productive. Had a good day. Talking to students at Friday Night Lab, and I found out like they had played all the DLC of the downloadable content for Elden Ring, and I haven't. Came out like at the start of the semester, and I haven't been too fucking busy. I didn't even buy it. They were saying like all the bosses are about as hard as the hardest boss in the original game. I'm like, holy shit!
Yeah, I heard you tuned up the difficulty. Yeah.
Like the hardest boss in the game just like curb stomped me like fucking 40 times in a row. Like it took hours to beat that bitch, and I had like a duplicate of myself helping me. Like had all the powers I did. It's called the mimic spell, it wasn't a cheat, it's part of the game. Has all your powers, abilities, it just doesn't. I think it can even pop potion, like it simulates doing potions, it's been a while since I played Elden Ring. But that bitch just fucking just beat the shit out of me. It was like. It wasn't even millennia if you played Elden Ring. Apparently they're all as tough as she is. I'm like, holy shit.
Is that Let Me Solo Her guy, boss?
What?
Oh, do you know the meme of Let Me Solo Her, from Elden Ring?
I'm sure it is.
Yeah.
Someone was so good at defeating her. That you could, you know, like those games, you can. Play like partially online, you're online, like you can go to each other's game, but you can't like all be together all the time kind of thing. But like. He would post himself right outside the door for the dungeon. Like anyone that walked up and said, please, I need help, like you throw down the symbol. He would fucking spawn in and he could just mop the fucking floor with her. He had her number, he fucking had her ticket.
Well, I was gonna say that.
He did it so many fucking times.
Well,
FromSoft, they send him a fucking sword. Like a real sword, like her sword, they fucking built her sword. He had like 1,000 assists or some shit like that, it was in the news. What were you gonna say?
No, I was just gonna say, I'm laughing because I feel like, yeah, I've heard that there are like some spell hacks in the game that like can totally body some of the bosses. Like in the magic tree, there's some weird spell metas that are like completely OP. But
There's some strong stuff, but even, yeah, I was playing a sorcerer, she still beat the shit out of me, it wasn't. I don't think he was a sorcerer, I think the dude that was helping everybody was a melee character, just knew how to fucking play. like was good at it. Alright, that gave everybody plenty of time to write this shit down. So let's get back to some math, let's look at an example, we're gonna let. X equal t squared minus 1. And we're gonna let y equal t minus 2. And we're gonna say t is going from -3 to 3. This is effectively what we did in the last section, polar graphing, where angle was the parameter. We're gonna say, we're gonna make a little XY chart. And have t there, and like, let's just run through them and plot what we get. Let's just do whole numbers. And we'll come over here and we'll make a nice big graph. And we'll plot them as we go. I'm gonna make a graph that has 10 going up and down. Just because I can see if I plug in -3 or 3, I'm gonna have a large number. Alright. Give everyone a second to get their table and graph ready. Alright, so for x, a little bit longer people are, I don't know if you guys are working it. For x, we have t squared, so it doesn't matter if I plug in -3 or +3, I'm gonna get the same answer. -3 or +3 is both, square those, we get 9, -1 is 8. That should be my x value for -3 and +3. If I do the same thing for -2 and +2. I get 4 minus 1 is 3. -1 or +1 squared is 1, and when I subtract 1, I get 0. And if I'm sticking 0, the t goes away, I get -1. This one is gonna just keep going up in sequence once we start it. -3 minus 2 is -5. -2 minus 2 is -4. -1 minus 2 is -3. And if you start to see a pattern and you think it's gonna stick, use it. It looks like this just keeps going up by 1. Rude. There we go. We need a beach ball just pass across the room when it goes up. Yeah,
You know,
it'd be fun, but like, since we get distracted and try to do it during lecture. Alright, so now let's just plot. If I go 8, I have a point in -5. That is t equals -3. At 3, I have a point at -4. That's t equals -2. When x equals 0, I have -3. That's t equals -1. And at -1, I have -2. So it looks like if I were to draw something along it, it looks like we're coming in like this right now. Oop. And the time is going this direction. And then when I go back, the next point is back to 0 and -1, so it's curving and coming back like that. That is t equals 1. At t equals 2, I'm at 3, 0. And at t equals 3, I'm at 8, 1. I think I have my point off a little bit. This should have been over here. This is definitely going one way. Generally, if I were to draw a curve like this, we would show it like this. Just to show that it keeps going on in both directions, but when you have something with a parameter, I would avoid doing that. I would keep the arrows going one direction to show the flow of time or whatever your parameter is. What kind of equation is this? It's a parabola, but when it's sideways, what's special about that? Anybody remember? Up and down, we have something like y equals x squared. When we're going this way, it's x equals y squared, or some variant of it. Let's see if we can get that, starting with our equations. Let's take x equals t squared minus 1 and y equals t minus 2. And figure out what that equation would be in terms of x and y. Any ideas on how I could do this? I know you all have taken algebra, have the tools, it's just been a while. And you may not have ever done it with something like this, but I know you can do it. Any ideas?
What do you want to do with it?
I wanna make it where t is absent, just y is a function of x. I wanna come up with whatever this equation is, and there's no t's in it. How do I get rid of t? And just make one equation. Set one of the equations equal to t, plug it in together, substitution. It looks like if I do it with this one, I'm gonna have some square roots, so fuck all that. So let's do it on this one. And I get y plus 2 equals t. And if I replace that up there. It looks like I'm getting x equals y plus 2 squared minus 1. In this format, this is like y minus k squared plus h, if you took algebra here. The vertex is at hk, so the vertex would be -1, -2. And sure as shit, our vertex is -1, -2. When it's y, when you have it y, it goes the other way, it's x minus h squared plus k. When it's solved for x, the letters switch. Are you already ready to go? Checking your clock? I'll mess you up, Lydia.
I just got a message, relax.
I know, I was just. I'll get some serious trouble, actually write this here and I'll mess you up. There are lines I can't cross. harassing or threatening students is generally one of those things that I can't do.
This situation. I mean, that's what I was kind of thinking, we probably smash those two equations together in some way.
Yeah, and we did.
So that's exactly what we do, is that what we do every time? This, we could just,
We can, but sometimes that's not helpful, as you'll see. Sometimes leaving it as is the easier way, like if you need to graph it. When you put them together, you're like, oh, hell fucking no. I promise you, it literally, if. The only reason you wouldn't say hell fucking no in your head is if you don't cuss. That's the only reason. You will see and be like, nope, I don't have any goddamn clue what to do here. But separately, they're like super easy, you'll see. As we saw with polar equations. Some of the things in polar equations in 8.7, they were really easy to graph in polar, but as soon as we put them in terms of y and x. They had square roots and squares and shit all over the place, and you're like. I don't even know how to go about that, I'd have to make an XY table and it would be work just to find y each time. Whereas in polar coordinates, it was just boom, done. You guys ready for more? Speaking of polar equation stuff, why don't we take a look at doing stuff in polar? Well, I'm gonna still call it T. X equals 4 cosine T, y equals 2 sine T. T is in 0 to 2 pi. P is the angle, it's a theta. Sometimes books leave it as T. If. It's related to time. That way you know it's not just an angle that's changing, it's actually, it's because time is advancing and what's happening there. So don't let T being inside the function trick you. So let's make a little table. I'm gonna do, let's do increments of pi over 2. If I need more points, I will. Nope, that's not 4, that's a 2. Go ahead and fill that out. We'll do it together in a minute or two. Alright, what happens if I plug these in? What should I get for 0?
40.
Pi over 2? Pi?
-40.
Pi over 2? 2 pi should be back to 0. Alright, so let's see what we got and then we'll decide if we wanna make more points. Looks like the lowest it gets is plus or minus 2 and x is plus or minus 4. You guys wanna have a couple more points? Think it'd be helpful? At least maybe let's do the ones in quadrant 1. Let's fill in like. Pi over 6 are 30 degrees. Let's do pi over 4 and pi over 3. Maybe we can get a little bit better of a feel. Is this making a diamond? Is this a rectangle? What's going on here? This feels like a calculator thing, at least for some of it. Cause I can have radicals, but that ain't gonna help me plot it, you know what I mean? Cosine of pi over 6 is cosine of 30. Or. I'm gonna write 2 decimal places. Sine of pi over 6 is 1/2, so that should just be 1. Sine of 45. Yeah, 1.4 here. And 2.82 over here are 83. And for this one, no, it's not gonna switch, cause. Like this, pi over 3 is 60 degrees, cosine is 1/2 there, this is 2. Times sine 60 is 1.73. Okay, so 3.46 and 1. Is like right there. That's like our 30 degrees or pi over 6. 2.83 is just a little left of 3 and we're right about there. That's pi over 4. And pi over 3 is at 2 and 1.73 is right about there. That's pi over 3. Now looking at it, it looks like it's doing like this, right? And since I know it's related to cosine and sine, I'm gonna guess it's doing the same thing going around. And the flow is counterclockwise. It's an ellipse. Now, the general equation for an ellipse is x minus h squared over a squared plus y minus k squared over b squared equals 1. Where a is the left-right radius kind of thing. And b is the up-down radius. Radius is the wrong word, but using things like major axis and minor axis isn't really helpful at this point. When we're thinking like this. Can we get that from what we have?
What is there a way to transform equations into that form?
What?
Go to take the two starting equations and transform them into that.
Yeah, we're gonna do that next. Just wanna make sure everyone's done with this. Alright, so let's look at doing that. Let's see if we can get it. If we do it right, the left right is 4. HK is still the vertex or the center. It's center on ellipse. So the center here is 0, 0 on our ellipse. And it's looking like A is 4 and B is 2. We should get x squared over 4 squared, which is 16. Plus y squared over 4 equals 1. That's what we should end up with if we do this right. If our parameterization, my graph that I plotted is correct. Now, one option is doing the solve for t and going from there. There is another way. It involves trying to do squaring them and taking advantage of cosine squared and sine squared and seeing kind of like what we have left over. Let's start with switching for t. Let's say x over 4 equals cosine t. So t equals cosine inverse of x over 4. If I make a triangle, cosine. I don't know why I did the left side so much. Cosine is adjacent over hypotenuse. So x over 4. With my angle being t right here. So that makes this part. Call that question mark right here and figure out what that's gotta be. X squared plus question mark squared equals 4 squared. So question mark squared equals 16 minus x squared. And question mark is square root of 16 minus x squared. So that'll be this side right here. So I've got y equals 2 sine t. What is sine of t from my triangle? What's sine of t from my triangle? Say that again?
Question mark over.
Question mark over 4 and question mark is. Square root of 16 minus x squared over 4. So that's my sine t. Which means I could, like, this is 1/2. The square root of 16 minus x squared. You guys good with that, cleaning up the 2 and the 4? So I'm gonna multiply both sides by 2 to clear that fraction. And I'm gonna say fuck that radical 2, so let's square both sides. What's the left side squared?
4y squared.
4y squared, don't forget to square the 2 as well. Excellent. Right side, the square just goes away. So if I add x squared to both sides, I got x squared plus 4y squared equals 16. And if I divide everything by 16. I get x squared over 16 plus y squared over 4 equals 1. Which is what we had up there, it's the ellipse. Let's see if we can figure out the other way to do this. If I square both of these and add them together. I should get 16 cosine squared t. Plus 4 sine squared t. And let's divide everything by 4 first. That helps get rid of the big numbers. Can I do anything with this? I don't know. I can factor out, I can separate that. Into 3 cosine squared t. Plus cosine squared t plus sine squared t. And that would give me a 1 there. I don't know if this is helping me any though. It's probably, I don't know what to do with 3 cosine squared t.
This is added together with the one cosine squared t.
I could, but then I still have, I'm trying to get rid of the t is the problem. I still have to go back up and use this. And that's gonna give me, I don't know if this is helping. Let me think about this. I'll think about it during break, we'll keep going and try some other stuff first. The cutaway definitely worked. Pissing me off, there should be something.
Wouldn't be able to set both the cosine and sine squared equal one with that lead coefficient of 4 on cosine squared, right?
Say that again?
So the cosine squared has a lead coefficient of 4 one step back. We wouldn't be able to set the cosine squared plus the sine squared equal one with that lead coefficient there, right?
Up here?
Yeah,
No. Cause they have to have some, they come to, it has to be a single one of each. That's why I deliberately separated it.
Couldn't somehow break this equation, two equations. So.
We don't wanna make more equations, we wanna make less. Let's come back to that one, let's look at some other forms of parameterization. Better use of our time, we found a way to get it. Doing the triangle. So like if we have y equals x minus 3 squared. Minus 1. Let's find 2 different ways to parameterize this. Now, one that always works, and I'm not gonna count this one because it's fucking stupid. We could just say x equals t. And that means y equals t minus 3 squared minus 1. But all we've done is change the variable there, so that one doesn't really count. But that's the kind of things I wanna do, I wanna make some swaps. So like, if I set t equal to what's on the inside. If I do t equals x minus 3. That forces y to look like t squared minus 1. And then if I add 3 to both sides. I get x equals t plus 3. I'm gonna use t1 here. To represent this one, because we're doing 2 different ways. So I'll use t1 for this one, this is one set of parameterizations. For that equation.
So like the x and y are the parameters, and it's these are the equations set in there. Set in. Like how calculated. It's kind of like-
T is the parameter, we're making a parameter. Yeah. If I don't know, let's see, if I added 1 to the other side, or both sides, I would have. Y plus 1 equals x minus 3 squared. I could say t equals this. So that y equals t minus 1. And this forces t to equal x minus 3 squared. Take the square root of both sides. And we can say x equals 3 plus this. Plus the square root of t. Maybe, I don't know, we might even need a minus there, I'm not sure. Squared, anything else we could do, that's one form of parameterizing it. That's something, another, so this would be like T2. They're different T's. The idea here is when we parameterize. Sometimes it's helpful to parameterize. Some parameterizations are better than others. Like. If that's option 1 and this is option 2. It's option 1, this is option 2. I like option 1 better. Doesn't have a square root. The idea here is like you get to pick, if you're gonna do a parameterization. You can pick how it's set up, but it has to work in both. Okay. Let's take a 10-minute break, it's 9 o'clock. Pause. So a second ago, I said, let's pause and put a pin in the x equals 4 cosine t. And y equals 2 sine t, because I knew there's an easy way to do it, and I was just fucking brain farting. The key is not to square first, the key is to divide and isolate the trig function first. X over 4 equals cosine t. Dividing by 2 here gets us y over 2 equals sine t. Square. And I get x squared over 16 equals cosine squared t. Y squared over 4 gets sine squared t. And if I add the two sides together. And we get our equation, and it was actually easier than the triangle method. I knew it was easier up, I just fucking totally brain farted the right order. That's so silly. And the next thing we're gonna do is the graph of the cycloid. The cycloid is annoying as fuck. But it models real life shit. cycle. Let's say we have a point on a wheel. On the edge of a wheel. Then the path traced. By that point. As the wheel rolls. Of course, along a straight line. We don't wanna go on around curves and wavy lines, just along a straight line. Makes a cycloid. And the equations that work with it are x equals. AT. Minus a sine t. And y equals a minus a cosine t. And t is negative infinity to infinity. Let's take a look at a specific example. We're gonna use a equals 2. So x equals 2t minus 2 sine t. And y equals 2 minus 2 cosine t. And let's plot out what's happening. As we go along. I'm gonna do 0, pi over 3, or pi over 6, let's do them in order. Pi over 3, we'll skip pi over 4. Pi over 2. Then 2 pi over 3. 5 pi over 6. Pi. Let's see how far that gets us, and maybe we need to do more points. That's so not what I wanna do. Yeah. Let's just make our table, and see how it goes. If I stick in 0 for t. X is 2 times 0 minus 2 sine of 0. 0 minus 0 is 0. And when I stick in t equals 0 into y, I get 2 minus 2 cosine 0. Which is 2 minus 2, which is also 0. And for this, I need to definitely have it in radian mode. 2 times pi divided by 3. Minus sine. Pi divided by 3. Not pi minus. 2. Shit, clear. Alright, just do. Pi divided by 3 minus sine. Pi divided by 3 and then double. I'm getting 0.36. For x. And 1 there, interesting. Yeah. I was plugging in pi over 3, not pi over 6. These are shifted down 1, those are wrong. Try that again.
And it's also like t equals 0 from y value is also 2, no?
What?
Y value for f for t equals 0 is 2.
No, it isn't.
2 minus 2 cosine 2.
Cosine of 0 is 1. So 2 minus 2. Nice try, crafty boy. Try to trick me. If I do pi over 2. Point 14. Two minus 0 is 2. Two point 46 here for that x. I hope you guys are doing them too in your calculator, because I've been known to fuck up my calculator. Four point 23. 4. What the fuck, I didn't do the y value there, like fucking scrub. Pi divided by 3 minus 2 cosine 2 pi divided by 3. Alright, we're not gonna graph it on this, we'll graph it on a piece of paper in a second. In fact, I'll pull out that evidence here right now and start plotting on
Isn't the Y value for 2 pi over 3 just 3?
it. The Y value?
Yeah.
Might be, I might have just fucked something up. It looks like that, right? Without using the fucking calculator. Yeah, just 3. Alright, so let's see what's going on. Finish that off, I'm gonna do. Increments of pi over 4. So I'll do 5 pi over 4. 3 pi over 2. 7 pi over 4. 2 pi. Those equations where I can see it again. There we go. So one full circle makes it do some shit like that. Which is modeling like the point is here. And then it's rolling and the point is here. And the point rolls along and it's up here. And the tile rolls forward, tires is rolling forward. It's over here and we get over here and it's in here again. Tires rolling. So it's tracking like if you had like a flashlight on a tire. Or a piece like you spray painted along the edge or chalk mark it. Where the chalk mark would be, if you had a fucking puncture in the tire, where's the puncture? And this repeats. It keeps doing this weird. Bouncy, 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 bouncy. It's doing that. That's cycling. I'm sure there are uses for it in engineering. Cause it is a point on a wheel and we do so all sorts of shit with things on wheels, like a tooth on a gear and shit like that. But I'm not an engineer, so
Was, so you can see this. Parts in the same space, like if there was a. You needed a. You would have to make it better, you'd have to notice like all the decisions at certain times. To make sure there was nothing in the way.
Right.
Stopping this.
right.
I think there's probably a really complex set of these equations when they're building looms.
I imagine there is.
Like parts running.
This is not the fun equation. This is the one I'm like, meh. It's got uses, it's just like, it's not bad, it's neat, it maps out a bouncing, like something that bounces without losing any energy. Basically, or a point on a wheel. But like, the plotting of it's the pain in the ass, by hand. Something that's much more useful is an object under gravity. Other applications of parametric equations. All the equations we've done of things being thrown into the air and coming back down. Where we're doing a parabola and all of algebra have always been the thing is going straight up and coming back down. And what we're doing is modeling its height as a function of time. So like. Straight up, straight gravity. Straight up and then down. We've been doing height, y is the height as a function of time. And in what are we doing, the imperial system? It's imperial. We have S naught plus V naught T. Plus A naught T squared. Where this is your starting height. Starting velocity right there. And acceleration. That's without having imperial, that's it without any implicit. But how often do we fucking throw something straight up and straight down? Like this, when we model it, it makes a parabola. But the axis here is t, not x. That's how we've been doing it before, so it looks like it's something thrown like that. But the actual flight of the ball is going straight up and it's coming straight back down. So that's not real, that's like really not what we do. We tend to shoot shit at an angle. So what are the equations that govern that? Well, it depends on the angle, right? Makes more sense that if I throw it kind of steep, throw it like not straight up, but like up high. It's going up, but gravity's fighting it really well. And it gets slow and it hits a peak and then comes back down and starts accelerating downward pretty quick. But if I really throw the fucking heat, a fastball, where like it's going forward super fast, the angle's low. Depending on how fast I throw it, it can cover a lot of ground before it hits the ground, like a fastball does. But if you just fucking, it just immediately falls, so like the angle matters. The things that matter the most on the actual trajectory. Throwing or launching at an angle. Important factors are starting velocity. Angle with the ground. And downward acceleration from gravity. And what we're really looking at is that angle is. That starting angle. If I made a tangent line. Like from the start, the starting angle is theta. When you release the ball, that's the direction that the velocity's going. And the ball actually comes back down because gravity, and there's no more force behind it.
And it kind of has that shape, usually most trajectories like this, because there's resistance from the air. Where it's like the ball increases velocity.
That will, it can, but like it's minimal. It does slow it down,
Usually it's more significant.
right?
But it swings.
If like, depending on the weather, foggy weather and shit like that, there's more shit in the air, there is more air resistance. The standard equations are. X equals V cosine theta. Times T. And Y equals V sine theta. Times T minus 16T squared plus H. So V is starting velocity. It is the angle you see. Angle at launch. With the ground. P is time since launch. And H is starting height. Time since launch, and this is in seconds. In starting height, this is in feet. So starting velocity has gotta be in terms of feet per second.
So T is lapse is like delta T. It's like, or it's elapsed time.
It's elapsed time. Delta T is technically true, I hate using that, cause as soon as you start Calc 1. Delta T means something very specific. But yes, it is the change in time.
That's good.
Well, most of the time you won't use delta T, you use delta X in calculus, so it's not too bad. So, we got 3 golf balls. Hit into the air at the same time. At the same time and speed. 120 feet per second. At angles. 25 degrees, 45 degrees, and 65 degrees. Which ball travels the furthest? Leave the ground. Like 3 different trajectories. So if we're going for when it hits the ground. What should be true when it hits the ground? Y should equal 0 when it hits the ground. So if we plug this in. Let's do that. So like, let's do the 25 degree. Y equals 0, that equals V, which is 120 feet per second. Times sine of 25 degrees. Times T minus 16T squared. And where does a golf ball start? On the ground, right? So H is 0. So what do I have here? 120 sine of 25. I'm getting 50.7 T minus 16T squared equals 0. If I factor out a T. I get T times 50.7 minus 16T equals 0. This is T equals 0 or 50.7 minus 16T equals 0. And if I solve for T there. I have 50.7 divided by 16. 20 sine 25 divided by 16. 3.17. Well, that tells me how long it took for the ball to get to the ground. I bring that equation back down from up above. If I wanna find x, I gotta plug in what x is, plug that t into the x. X equals 120 cosine 25. Times that t, 3.17. And we're getting 344.7 feet. Then we do the 45 degrees. It looks like this is gonna be 120 sine 45 minus 16t equals 0, if I look at what I did before. So t equals 120 sine 45 over 16, that's like the shortcut way of doing this, we can speed up 65 degrees if we do this next time, just change the angle. 120 sine 45 divided by 16. I'm getting t equals 5.3 seconds, so it flies longer. Does it go as far? X equals 120 cosine of 45 times that t. $450. It went further. Fucking exactly 450. And if I do the 65 degrees. I'm gonna speed up and use this and just modify it to say 65 degrees. 120 sine of 65 over 16. Is about 6.8 seconds. So x equals 120 cosine 65 times 6.8. And we're getting 344.7 again. For distance, the 45-degree angle was best of these three. When you take a calculus-based physics course, you will find out for sure that that is the best angle no matter what. 45 degree is the optimal angle for a launch if you're going for distance. That's my fucking phone blowing up my shit. Alright, let's do one that's like this, but we're gonna need these equations. Wait, does anyone need that page longer? Okay. I'm gonna keep these equations here, cause now we're gonna look at converting to rectangular coordinates. But we'll choose like a simple, let's make the numbers a little smaller. Let's say a toy rocket's fired. At 45 degrees. With a velocity of 36 feet per second. Let's find the rectangular equation. So I'll start with the x one, x is 36 cosine of 45 t. Which is 36 times √2/2 t. So x equals 18 √2 times t. So if I divide both sides by that 18 √2, I got x over 18 √2. Which is x √2 over 36 if we rationalize it. We look at the other equation, we've got y equals 36 sine 45 t minus 16 t squared plus h. Let's say it's fired from 0, so plus 0 for h. Cause you're not gonna fire a rocket from your hand, you're gonna have it sitting on the ground and just launching it. Right, that makes sense. So this is 18 √2 again. After we simplify that, minus 16 t squared. And we can plug that in. In fact. If I use the first form right here. Look what happens. The first part just cancels out, we get y equals x, that's pretty nice. That's only gonna happen at the 45-degree angle. And you get minus 16x squared. I'm gonna do this as this, so like 18 √2 squared. I'm gonna do this as. I don't know, 9 times 2 times √2 squared. Which is 81 times 4 times 2. Which makes this a little easier for me to cancel out. This is 8, so 16 over 8 will give me a 2 on top. Is that, did I fuck that up? Let's see, 18 √2 squared is 648, and then 81 times 4 times 2 is also 648, so that's correct. 9 squared times 2 squared times √2 squared. So y equals that. I put the squared part first, I get that. And we did it, we got it in rectangle form. Jordan's squinting on me, what I do,
I'm just, looking at. The negative two, over 81x squared, but I just see over, just kind of swaps and sixes on.
so I did this squared, I did it over here, leads to here. Leads to here, leads to here, and that's what I put in. Because that's easier for me to simplify with the 16. If I did 16 divided by 18 root 2 squared, I'm gonna get some fucked up decimal that equals 2/81. And I'm not gonna recognize it for the simple fraction that it is. So I try to avoid switching decimals whenever possible. This is exact, any decimal form is gonna be off, and have to round. Bam, there we go. Now you could, you factored out the negative 2/81. You could complete the square here. To get it in the format or the format of a parabola. That format would be negative 2/81. X minus. It's that divided by 2. Should be 1/4 squared. Plus something, and the something is what you gotta calculate. Completing the square will. Help you find that. But we don't have time, it's 10 AM, so I won't hold you any longer. And that's not necessary, we did get it in rectangular form up there. That's it for new content. That's all we got. Isn't that fun? Isn't that
Yeah.
everything, hoped it would be,
You gonna do your Saturday, Mesa, or?
I am gonna do my Saturday Mesa, I will be there this Saturday. I can't encourage my students to work over Thanksgiving break if I'm not willing to do the same. And I will have a practice exam up for you guys soon. If not today, by Wednesday.